Hello, my name is Charlie Ward, and I am doing this project preparing for the quantum decryption wave for my Cyber 332 computer security class at Metropolitan State University. My professor is Dr. Masumi Munmun, and I'm doing this for the Department of Computer Science and Cybersecurity College of Science. Sorry, so this will be uploaded to YouTube, and I hope you enjoy it. So I need to put a disclaimer out there first. This video is for educational purposes only. I am not liable for any damages that could be caused during these demonstrations. I don't think we're doing anything particularly dangerous. My demonstration will be using Qiskit, which is IBM's quantum computing language. But really, there's nothing more dangerous than that, unless you count like spooky math. So we'll see. Yeah. So we're basically what I'm doing is an introduction into quantum computing. No, sorry, I'm not doing an introduction to quantum computing. What we're doing is an introduction into quantum secure algorithms, which are hopefully going to secure our computers once quantum computers are able to fully use Shor and Grover's algorithms to decrypt. That is the basic idea of what people are worried about, is that classical encryption will no longer be safe once quantum computers get to a certain level of effectiveness, right? So basically what I want to introduce quantum computing in general. It's a mix of quantum physics and computer science. So we're talking about harnessing subatomic particles to power computers. Subatomic particles move in a way that is very different from what we think of as classical physics. So when you get down to like quarks and neutrinos and electrons and protons, they operate fundamentally differently when they're moving through space than what we think of as normal. It's what Einstein called like spooky, right? It's very weird. It's very strange. So we want to specifically talk about the quantum state, which these particles can be put in. It's very important to understand superposition and entanglement, which are two of the spookiest aspects of these quantum particle physics. So let's get into that a little bit. Nice. So when we think of classical bits, we think of ones and zeros, right? We think of it's either 0 or it's 1. When we talk about superposition, when we talk about qubits in a way that are in superposition, they exist as both 0 and 1. They exist as a probability specifically, right? I'm sure most people are aware of like probability and statistics, discrete math, if you're in this class, right? So we're talking about both 1 and 0 at the same time, because this is fundamentally how quantum physics works. Motion isn't A to B, motion is a wave. The classical example of this is to think of a qubit or a subatomic particle in a maze. It doesn't go from start to finish, it takes every route simultaneously because it is there's a probability that it will take each route, and it takes each route all at the same time. This is very strange to understand, but the theory has been around for a long time. I think most people are aware of Schrodinger's cat. The idea, if you put a cat in a box with some poison, and the poison will for sure kill the cat in an hour, slow acting, it might kill the cat quicker. So you put the cat in the box with the poison and you wait 30 minutes, and then is the cat alive or dead? Well, the cat is both alive and dead until you open the box. So that is what we think of as entanglement specifically. That's how we can introduce it, because entanglement is the idea that these states of being, the state of the cat being alive and the state of the cat being dead, affect each other. There's a probability that both exist, and they both do exist until you open the box, until you take a measurement of one or the other. And measurement is very key in understanding a lot of this, but we won't go too deep into it. But entanglement is the very idea of one particle having such a drastic effect on the other. I don't want to ramble on too much about this, but this is the fundamental idea that harnessing many of these qubits together, entangling many of them into a state of coherence, can create one single logical qubit, which is kind of the basis for adding more processing power to these machines. Again, this is a little bit over my head, but these fundamental theories are both interesting and very important to understand as computer scientists and cybersecurity practitioners. Let's do a quick demonstration. I've downloaded Qiskit, which is IBM's quantum computing coding language, just to kind of show you how these things work. Here's this. I'm going to be using the Qiskit test 2, but I made some notes on this. Basically, all we're doing is we are putting qubits, we're creating qubits and putting them through quantum gates, which essentially puts them in a state of superposition first with the Hammerhead gate, and then we put them through a C0 gate, which will put them into, a state of, a state of entanglement. And like I was saying earlier, I don't want to go too into this because I already talked about it for another class, and we've got more important things to talk about right now. But a state of probability where taking the measurement of one will essentially affect the other. If we think about states like this, here are four states of being. We talk about A, B, C, and D. We don't need to go too into this again because we have other things to talk about, and I don't want to self-plagiarize myself by going back over some of this. So essentially what we're doing is we have this at the end, which is basically the probability. After we add the probability amplitudes, which is basically squaring each of them, we have them in a probability that A is 1/2, or like 50%, and D is 50%. But if we take the measurement and it turns out to be A, then it can't be D. And if we take the measurement and it turns out to be D, then it can't be A. So taking the measurement of one has a specific effect on the other's existence, basically. And this can be done over light years distance, theoretically, right? So this is what I'm actually going to be running, just because I had some issues with the AER simulator from the other thing. So here is my command prompt. I had to put it into a virtual environment. This is what you see here, just so that I could run it just kind of in a container. And all I'm going to do is run this Python script, which is, again, this, which, if I remember what it's called, we do this, we wait, and what it should do is give us back a probability of both of the state vectors at the same time. Hopefully. We'll see. If it doesn't work right now, I apologize. It should work. It's worked before. Maybe it's not working now, which would be pretty sad because I would have to do the whole presentation over again. There it is. It worked anyway. So it looks like it didn't run through the C0 gate. So it's just giving us 3, which is position C, or no, I'm sorry, it did run through the C0 gate. Oh my gosh, I got my math wrong. It's at position 3, which is D, the state vector D, about 49%, and at position 0, which is position A, it's at 50%. So basically these particles exist in themselves as both at the same time, which is very interesting. I will not go any further than that because this is already a complex topic. So let's talk about encryption. Classical encryption today, I typically look at RSA. This is the one slide along with the demonstration that I used in the other presentation. So That is this. I cited it at the end. You can see my references. This is our encryption for RSA. This is what we call a discrete logging. This is an example of integer factoring and a discrete logging problem, which classical computers are not good at handling. However, quantum computers are very good at handling. So with enough processing power, these quantum computers will be able to break this. Stop it. And since this is basically the math that we use to keep everything secret, it's going to be very bad. Most nation states are operating, especially like the superpowers, the US and China, are operating under this policy of like gather now, decrypt later, which I think Faisal told me once. So basically what everybody's doing is they're trying to scrape as much data and information as they can right now, even if it is encrypted, so that when quantum computing comes around, quantum decryption comes around, they'll be able to decrypt all these state secrets, or business secrets, corpus secrets, whatever, you know. So this is done with very large numbers. Usually we think of them as composite numbers, which are, oh my god, even prime numbers, I want to say. Oh god, don't quote me on that. Yeah. But again, with Shor's algorithm, with Grover's algorithm, both this and basically like brute forcing can be done exponentially faster. So we need basically what the NIST is doing, the National Institute for Standards and Technology. I almost said Science and Technology. What they're doing is basically creating kind of these round robin tournaments almost to try to find new quantum secure algorithms. And a lot of these are graph based because quantum computers are not as good at solving these. Actually, they're very bad. I know these look complicated. I'm just going to touch on them a little bit. If I had to suggest any of them, I would suggest lattice based encryption because it's the most interesting in my own opinion. And basically all it's doing, as you can see here, oh my gosh, wow, that's really annoying, is it's taking vectors and basically what you have is a common array of vectors set that everybody uses. An array, if you think of like programming, is just like a set of elements, right? In this case, the elements are the vectors of varying sizes and degrees. You can do this over it's always done over a finite graph, but it can be done over different dimensions. Typically, you think of like 2 dimensions, x and y, but you could also you could add a z. You can make it 3-dimensional, which would make it even more secure, ideally. Again, just touching on this stuff, if Alice wants to create a private key, and a public key, what she does is she uses this formula here, b equals s times a plus e. S is her private vector, her secret vector, which is also her private key. A is the array that both her and Bob, who's going to receive this message, have. E is a tiny vector, which is the error correction one. And then B, the formula together, is the public key, so that's what she shares. Bob is able to decrypt this with enough error correcting techniques. And it gets a little bit more complicated than that, but these are solvable. These are practical. This is kind of the biggest or the most highly looked at one right now, and you can combine lattice-based encryption with some other ones too. So yes, sorry, what we're doing is basically finding the okay, I'm just going to move on because there's no need to go into it further. I am just going to embarrass myself. Quantum secure zero knowledge proofs are also very interesting. Let me move myself down here. No, actually, I'm better up here. Quantum secure zero knowledge proofs have been a thing in crypto for a long time. They have potential to get into quantum, though it's still a little bit iffy on if they're going to or not. I find the theory of these pretty interesting because they operate on the fact that nothing is shared, so nothing can be stolen, kind of, or nothing can be decrypted. It's a little bit complex, but let me try to explain it. Maybe I'll just read this quote first. A zero-knowledge proof, ZKB, is a method of proving the validity of a statement without revealing anything other than the validity of the statement itself, right? So if I'm validating your credentials to me, and I want to know something you have, right, or something you know, something you are, which is like the basis of credentials checks today. Something you know is a passcode, something you are is like your fingerprint or your retina iris. Sorry, that was weird. But yes, that is what that is. Sorry, I lost my train of thought. I want to know something you are, but you don't have to actually present it to me. I just have to verify the validity of your statement. I just have to verify that what this is what it is to you, basically, which is a little bit annoying to explain, but I promise you that it is interesting. So at the end of the day, you are not sharing with me anything that you know or anything that you are. I just know that you're being truthful about it. So nothing can be shared. So nothing is shared in it other than the validity of the statement. Again, a little bit weird. Not all the way there yet, but it is getting there, and it is also very interesting. We have the next two are both graph ones as well. There are multivariate equations. Oh my god, this is the first time I said it correctly. Multivariate equations are basically using multiple quadratic equations on the same graph in order to basically figure public keys, right? So and in order to figure private keys as well using these public keys. So what we're talking about, and I can explain this better on the next slide, but what we're talking about is basically using multiples of these in order to figure out other ones. Yes, sorry. Let me explain this better on the next slide. These are elliptic curve cryptography, which are classic, as you can see here with the Mordell curve. Mordell curve, I'm sorry. Basically, we're talking about these specific kind of elliptic curves, which are going to be put together in order to find. They're put together through tunnels, which is what the isogenies are. Okay, let me explain this in a way that is less complex. We have one graph here, which actually I'm going to show one other thing. I like this website called Wolfram Alpha. Elliptic curves. I spelled it wrong, I'm sorry. So these are examples of elliptic curves, right? This is the Mordell curve that we were looking at before. We're going to specifically be looking at these kind of curves here. And what we're basically doing is we're taking things called isogenies to connect one to the other. And quantum computers are very bad at this because of the way that the graphs work. Each of these graphs are like a collection of points, and we're taking 2 points on 2 different graphs and connecting them through tunnels or bridges, which are the isogenies. And the isogenies are basically the keys. So it gets very complex, and it's not completely figured out yet, but it is getting there. And again, I don't want to go too deep into it because I will just embarrass myself, but these are all of the ways, these are some of the ways that the NIST in the US is looking at securing their encryption for everybody when quantum computers become more practical in 20 or 30 years, right? That is pretty much all I wanted to talk about. We talked about the basics of quantum physics and computing, how quantum computers differ from classical ones, superposition and entanglement, how it was simulated. We used the Qiskit thing, right? Shor and Grover's algorithms. We didn't go too in-depth on that, but the basic idea is still there of them being able to be harnessed by quantum computers to break classical encryption algorithms. And then we spent a little bit of time talking on quantum secure algorithms that the NIST is considering in the future. Again, I apologize, my explanation was not perfect. These are very complex topics. Hopefully that my explanation will be better next time. So yeah, you can add me on LinkedIn. Here's my references. Yeah, I did a lot of research to this, so I'm pretty proud of it. And then this obviously is my own with, yeah. So yeah.